we speak. So it is represented like V comma E. So you'll have set of vertices and set of edges. And this is an example. Here I have how many vertices? Anyone can interact with me, I hope. Yes, 6 vertices and have connected with lines. How many lines are here? Yes, yes. So now today, for today's lecture, I'm just trying to give you a glimpse of one algorithm which gives you shortest network distance, okay? So at the end of the session, I'm planned to give one practice problem, okay? Just try to follow it. It is very simple to do also. Yes. So this graph means a connected vertices and lines should be connected and you get a proper structure. So next we have a cycle graph means you'll have a cycle-like structure. Here you can see one square term and the another one is without any, I mean, we have 2 cycles here, one triangle and one square, okay? So acyclic means you don't have cycle here. So this is tree. Here, you don't have cycle. Okay, any acyclic graph is called tree. Spanning tree means from a cyclic graph, I can extract a spanning tree. Okay, so you can have any cyclic graph. From the cyclic graph, you can leave few edges, but I must connect all my vertices so that I must get a graph, and that graph is called spanning tree. And this is weighted graph. Weighted graph means for each edges, I can give weights from each, I mean, for connecting edges. For example, if you want to travel from Tirupattur to Arcad, you know certain kilometers, yes or no? Yes, so you can take Tirupattur and Arcad as vertices and the connecting line in kilometers as edges. So this is how the network works, okay? So the weights here gives you the validity of that network, okay? Yes. And from weighted graph, I can find minimum tree. So this is the left side is your weighted graph. From there, I'm removing few edges and I'm connecting my vertices and the resultant is my minimum spanning tree. I can have more than one spanning tree for this, but among that, which gives me the minimum weight will be my minimum spanning tree. Okay? Yes. And so today, I took Kruskal's algorithm to give you a minimum weight distance, minimum distance from one point to another. Okay, it goes like this. The first step is that, so you have to travel from one point to other, and I must travel all the vertices. And every time when I travel, I must not form a cycle. If I form a cycle, I must skip that place and I have to move on to another vertices, okay? Yes. So this is the graph, and for this graph, I'm trying to find minimum spanning tree, okay? So that is minimum distance I can travel, I must find that. So for this, I can start from anywhere. First, what I'm going to do is I'm going to arrange my edges in ascending order. That is from minimum weight to largest weight, okay? So this is how I'm arranging my edges. So I took all my edges. What I did is I arranged all my edges in left side, in ascending order. Okay. Each time I'm going to stick my edges in my graph such that final graph must be a spanning tree and it must be the minimum spanning tree. Okay. Yes. And so using that algorithm, first minimum weight is 1. So I'm connecting that. Next is 2, I'm connecting H and G. Next is 2 again, CE. Next is 4, so I'm connecting BA. And next is 4, I'm connecting CG. And next is 6. If I connect my EH, I'll be getting my cycle. Yes or no? Here my cycle is CGH. So I must not do that. So I'm skipping that. I'm removing that edges. I'm going to connect some other edge. So I'm connecting next cycle, that is next line, which is CD. Now again, next is CI, next weight is 7, which is, again, I'm getting a cycle, which is CGHIE. So remove it, go for next. So if I go on, I'll be getting my minimum spanning tree to be this, and weight of this minimum spanning tree is 37. Okay, so for the given graph, back. For the given graph, my minimum spanning tree is this, and the minimum weight for this spanning tree is 37. Okay, so this is actually graph theory. That is, you are connecting your vertices and edges. Okay, but in every cases, we cannot find our weights. Okay, there are few cases where the edge weight can be what? It can be uncertain values. Okay, in that case, we move on to fuzzy graph. So fuzzy graph says, so here again, you're going to play with vertices and edges, but here, my vertices, we have to follow a certain rule. That is, my edge value must be always less than or equal to my minimum of the edges, vertices. Okay, you can see here, see A and E are connected here. See, 0.6 and 0.5 is my value. My edge value is minimum of those two is 0.5 and less than that. So I must choose 0.4. Less than or it can be equal also. Okay, so this is my uncertain cases. I can use fuzzy graph to find the shortest distances. Okay, and the crisp graph for that is the right side which I given. This is actually, the right side is a just crisp graph. That is, you have vertices and edges, but no restriction about your vertices values or edges values. Okay, but in the left side, we stick on to the values between 0 to 1. Okay, yes. So an application for this fuzzy graph is, suppose if you have a network, for example, whole of Tirupattur district, okay? I want to cash load to a particular bank, okay, from one place to another. For example, you start from Secretariat and travel around, and I must get back to Secretariat also, okay? In such a way that I must cash load in every places in a minimum distance spanning time, okay? And as you all know, when we travel, we'll be using kilometers to travel, yes? So first, to get this up, minimal time to find the minimum distances, first you convert all your values to falsified value. That is, you'll have all your weights in kilometers. You convert that to falsified value, that is 0 to 1. Okay, and then you use Kruskal's algorithm, or you can use any other algorithms to find your minimum distances. And this is the kilometers, and this is all the sites which I took. This is actually a particular area in Velachery in Chennai. So offline and online sites we took. And the network is this. From one site to another, I can do 15 different routes I can go. So the network is this. But among this, I'm converting all my kilometers to falsified values. Okay, that is between 0 to 1. Okay. And when I use the algorithm, I'll be getting my networks to be this. So if I use this particular order, I can cache load all my ATMs in that particular area, and I can use the minimum kilometer, which is 31 kilometers. Okay, so I hope I gave something new to you. That is, we started with graph. That is, you have networks in everywhere. And from there, we took a simple algorithm, Kruskal's algorithm. From there, we took what? Uncertain values, uncertain networks. From uncertain networks, and we can find minimum distance, and which we got is here is 31 kilometer for the cache loading. Okay. Yes, thank you. And I gave you a practice problem. If anyone can try and tell me. Did anyone try it? Are you trying actually? Yes. Anyone tried?